Hey, what's up, everybody? Sorry we have to do this way on the computer like this for this week, but hopefully it will go a little bit faster. I'm going to go through these lecture notes on regression, and so I will have these posted on YouTube. You can, of course, ask me any questions over email, and I can try to get you an answer to those. So I'm going to go ahead and jump into the slides, and we'll try to get through this pretty fast. So you're watching this, I know you want to get to the punchline so we can get through. So here's our first set of reminders for this week. Your homework number 8, which is about ANOVAs, is due on Monday, March 28th. I don't know when you're watching this, but if you're watching it on Monday, it is today. So the last day to schedule the makeup exam is also on Monday. If you're going to know you're going to miss next week, next Monday, then I need to have that request in by Monday. And then there's a participation quiz, number 11. It opens up on a Monday, and it runs all week. I can't possibly grade them or look at those, and I wanted to give plenty of time. And this is the last amount of a quiz stuff you'll need to know for your test on Monday, so it's due on Sunday. And it's 4 questions about two-way ANOVA. And then, of course, a week from Monday on the April 4th is your second exam, and all the same rules apply as before. We're going to be there at 8 p.m. at Elliott Hall. There's going to be a TA review session beforehand, and there's an announcement in Brightspace about that. If you didn't see it, you can find the time and the location and all those details are there. And I also mentioned in that same announcement, I'm going to do my office hours like I did last exam. In each class, I'm going to roughly go over the same questions, whatever class time allows in our 50 minutes. And in that extra time, I will go over additional questions or questions you may have to get you ready for the test later that evening. So today we're going to do Chapter 2 about linear regression. So a linear regression is where you finally start to look at the relationship between two quantitative variables. So we may have studied, let's say, does exercise reduce cholesterol? And so we look to see, is cholesterol reduced is what we've looked at so far. We don't necessarily look at the exercise and quantify the exercise, right? We just say we're going to make some people go through this exercise program, and it's all going to be the same exercise. You're going to run 1 mile every day and then check your cholesterol after a 3-week period or something. And we just look at the cholesterol. What we're going to look at today is look at both variables. What if I change the exercise and some people get a lot more exercise, and then see what happens to their cholesterol and see is there a correlation? And correlation does make a lot of sense. These things exist everywhere. Do tall people have big feet? And there's some proof for that, right? As we've discussed in examples in class before. Is there a relationship between your weight and your blood pressure? And there probably is if you studied that. So what we do is we do a scatter plot for these, and we try to describe the form and direction and strength of the relationship. And we can summarize these things using SPSS. This is another pretty calculation-concentric set of steps we're going to do, so we're going to use SPSS, but you can go back to using a graphing calculator here, and even my little simple $10 calculator can do this kind of work for us. So first slide here, scatter plot. A scatter plot is where you just basically throw all your data, your X's and Y's on there, and you put little points for them. It's called a scatter plot because the data can tend to be scattered. All right, so we put the explanatory variable on the horizontal axis and the response on the y. So if you think that, for example, in the case of exercise and cholesterol, does cholesterol make your exercise change, or does exercise make your cholesterol change? Think about that. So the response is, the explanatory variable is exercise. I change my exercise, and the output of that, or the thing that is a response to that, is my cholesterol. It doesn't go the other way. All right. So we plot all these different exercise levels. Somebody exercised for 30 minutes, and here's every day for 3 weeks, and here's their cholesterol change, or whatever the number is. And we plot those, and we do that for lots of sets of data. So we want to see an association between those two, and this is what we call the correlation. And we also want to know if that one variable can tell us something about the value of the other, so we can use that to predict something and create a regression line. So you can say, look, I've done this study, and so if someone is 6'5", then I can predict their shoe size to be 13 or 14 or some number such as that. And so that's what we see with regression. So the first thing we need to check, though, is the correlation. Are these variables correlated? And if they are correlated, then we can go further and talk about a regression line. We can do both calculations, but the regression line is only valid, that we find is only valid if there is correlation. It's similar to having a hypothesis test, and if you find alpha to be some number, then you can continue and make claims and that kind of thing. Similar to what we did with ANOVA. If ANOVA finds there's a statistically significant result, then you can go on further and do the Bonferroni. It's similar to that. So when we look at a scatter plot, what we look for is form, direction, and strength are the things we're looking for. So form, is it roughly a straight line? Does it follow a linear pattern? Now, it doesn't have to follow a linear pattern. There are things that have, say, a quadratic relationship. You can study the velocity of a parachute falling, and that's not a linear pattern. That's going to be a quadratic pattern, for example. But for the sake of this lecture and what we're going to do in this class, we're going to just work with linear patterns. The direction. So some things are positively correlated. We expect that if someone is taller, that their shoe size would be larger. So when height goes up, we expect shoe size to increase with it. There's negative association, which is the one example we used earlier with exercise and cholesterol. If your exercise time increases, we expect your cholesterol to decrease, and that's what we call a negative association. There's no connotation here about that it being positive or negative in the sense of the word, that it's a descriptor. It's the numerical positive and negative just means that one goes up and the other goes down. And then strength is determined by how close the points lie to a simple form such as a line, or if it is a quadratic or some other shape that's mathematical. We would call that a strong correlation if it's very linear, and if it's not like a straight line, we would call that weak. We'll get into more details on all of these, of course. So here's an example from the textbook about osteoporosis. And so this is a really cool study. I'm actually intrigued by this study, where we use our dominant arm more than our non-dominant arm. So we expect when measuring bone strength to find stronger bones in the dominant arm. So this table below compares the bone strength in arms of 15 young men. And you can see, as we look here at our data, we have, it looks like, as I'm examining here, it looks like mostly the numbers on the non-dominant arm are smaller, as we might expect. And so we're going to see, is there a correlation between this? And so here's what a scatter plot looks like. It's all those XY combinations. So if I go back to the previous slide, 15.7 and 16.3. So 15.7 is my X value and 16.3 is my Y. So if I go over to 15.7 and up to 16.3, it looks like that might be that data point about right there, that little red dot you can see there. And so every one of those data points are plotted in an XY pair. And so the form, it looks like these points are kind of doing a straight line. You see, it's not perfect. There's not one line that will go through all the points. But it does look to be roughly straight. It's not a curved shape or some other mathematical shape we might see in a graph. The direction is a positive association, so we see as the bone strength in the non-dominant arm goes up, we see the dominant arm strength also goes up as well. And the strength, we would say here, is quite strong because the line that goes through there does appear to be very close to all of those points. So here's an example of roughly a straight line, and it's a linear pattern. And this one has a negative association. So you see, I don't know what these variables are, but as you see, as the X increases, the Y is decreasing in this case. And we say the strength of that one is strong as well, because it does tend to approximate a very straight line. So when we want to set up a regression case, we do our scatter plot initially just to see our form, our direction, and our strength, and are there any outliers. Outliers can really mess this up, so we have to look for those, and we study for correlation. And if the pattern is linear, we can get an equation for that line. If it's quadratic, we can get an equation for that, or some other function. You can get equations for any kind, but we are, again, studying just linear. And we'll look at the normal probability plot and the residual plot as well. So the linear relations are important because a straight line is a simple pattern that's really quite common. And so correlation, R, measures the direction and strength of the linear relationship. And this big ugly thing here shows you how the mathematics is done. It's like doing standard deviation, but even more difficult. And so this is definitely a situation where we use technology. You would use a calculator. And again, my little small calculator, I don't have it handy with me right now. It can even do this. So you don't need SPSS necessarily. Of course, you will be asked to interpret SPSS and do that for your lab, but You can do it with other tools. So the properties of the correlation. R is this letter R is an average of the products of the standardized variable, and it doesn't matter which one you call X and Y for this. In a minute, it's going to matter. I said earlier, we said that exercise reduces or changes cholesterol, but cholesterol does not change your exercise level, right? That doesn't cause the other. So when you're calculating R, it doesn't matter which one you call X and Y, and you can kind of see maybe from the mathematics of that which one's X and Y. It really doesn't matter because this is a product, and of course 3 times 4 is the same as 4 times 3. That's why it doesn't matter here for this. In a minute, it will matter. R has no units, so it doesn't matter what your units are. If you change everything from inches to centimeters, it doesn't matter. So R is positive. It's a positive number when there's a positive association, and it's negative when there's a negative association. This is where we get that description of positive and negative. R is always a number between -1 and 1. So R near 0 indicates a weak linear relationship, and if it's close to -1 or 1, it indicates a strong linear relationship. We're going to see some examples of various values of R and what their graphs look like here in a second. It measures the strength of only a linear relationship between the two variables, and it is not resistant to outliers, much like the mean and standard deviation are also not resistant to that. A few outliers can really, really mess this up. So here's an example of correlation. So you see an R of 1 is a perfect correlation. You see all of those dots on that scatter plot are perfect straight lines. This would be trying to say you did a scatter plot of the distance traveled of someone that was going 60 miles an hour, exactly 60 the entire time, and you had a bunch of different times and wanted to know the distances. It's a very perfect correlation. If you've traveled 1 hour, you've gone 60 miles. If you've traveled 2 hours, you've gone 120 miles. So some things are perfect correlation. And as you see, as R starts to go down, the data are still aligned, but the spread between them increases until you get to 0. And 0 almost looks like a shotgun blast on a wall, where the points, I can't tell, is it going up, is it going down? And honestly, at point 2 and even point 3, I can't tell, is that line going left to right, going up? And then as you see, as it starts to increase again on the negative side, and we get a higher negative number, it starts to come into more of a form, and now the line looks like it's going down as we go left to right. And so you see a correlation of, perfect correlation of +1 is a line going left to right. As we go left to right, the Y values go up, and a perfect correlation of -1, as we go left to right, the Y values go down. If scatterplot shows a linear relationship, we want to summarize that by drawing a line. So you could draw a line by an eye, but that's not a good idea. We need a method to do this, and so we do a least squares regression line of Y on X. And what that line does, it is a line that makes the sum of squares of the vertical distances between the data points on the line as small as possible. Okay, so here's an example of, for the bone strength study, here's a line, and so what we're talking about, this vertical distance, we find out what that distance is and we square it, and we want a line that minimizes the sum of all of those squares, and that's what this process does. If you thought the regression calculation was complicated, the one for this is insanely complicated. I've taught stats before, and I've had it on a formula sheet, and I've always laughed at that because I think who is actually going to try to run that calculation by hand? No one ever. And so the least squares method minimizes that vertical distance between all of those points to try to get the line as close as it can be to every point at the same time. And so in the case of that bone strength, the equation of the line is written as 2.7386 plus 0.936x. So let's go back and talk a little bit about some baby algebra here. Hopefully you're familiar with the term of the slope-intercept form of the equation, which we say is y equals mx plus b. Hopefully that's an Algebra 1 thing from some point in your mathematical career you might remember. When we do that with linear equation, we have that same thing going on here. Some different software does it as b plus mx, as this is doing here. So the slope is this number right here in front of x, if you recall from what mx plus b is. This is indicating how much as your non-dominant arm increases in bone strength. It's saying your dominant arm increases by 0.936. So every unit of 1 that I increase my non-dominant arm, I expect my dominant arm to go up by 0.936. and then the 2.7386 is the y-intercept. And this is kind of a phony thing, honestly, because that's saying if you had 0 non-dominant arm strength, you would have 2.7386 in your dominant arm. It's not a realistic case because there is a minimum to these arm strengths, so they would never get to 0. But for mathematical purposes, we do need to have a y-intercept to define the location of that line. And so we find this equation, as we said, instead of y equals mx plus b, it's more like y equals b plus mx. And we also don't use b and m as we do in algebra class. Some statistical software uses a plus bx. Some use b plus ax. And our textbook is using b0 plus b1x, where b1 is this and b0 are these various things here. And so again, we say the b1, the number in front of the x, is the slope, and the b0 is the intercept. And in this case, the slope and intercept of the least square line do depend on the units of measurement. So we said earlier for regression, if you have your units are in inches and then you change them to centimeters, it doesn't matter. And it doesn't matter to find r squared and r. But to find this equation for the line, it does matter. And this is also where the order matters. So we said exercise reduces cholesterol or causes the change in cholesterol. And cholesterol does not cause a change in your exercise. It doesn't work the other way. To find r, that doesn't matter, but to write this line, we have to have them in the right order. So in the bone strength study, we have x bar is 16.01, our y bar is 17.73, standard deviation of those numbers there, and our r is 0.905. And so we can, if we have those numbers, we can generate that formula. And so we say b1 is r times sy over sx, and we get that's 0.936. And b0 is y bar minus b1 times x bar. You run those calculations and you get the 2.745. And that's the same as we obtained earlier with the software. All right, so that's one way to approximate that. Some facts about the least square regression line. There's a close connection between the r and the slope. If r is positive, as we talked earlier, the slope is positive. Of course, that means that line is going, or if you're looking at my screen yet, but it's going up as we go left to right. And if it's negative, it's going to go down as we go left to right. It always passes, the regression line always passes through x bar, y bar, based on the definition of that. It's just kind of a little fun fact, not necessarily something you need to memorize, but the distinction between explanatory and response is important in regression, as I just said. Exercise is the x and cholesterol is the y, but it's not the other way around in this case. So the r squared, once we create this line, it is our number that helps us decide, is this line really a good line? Is it something we can take to the bank and use to make predictions? And so we take this by finding the variance of the predicted values of y hat divided by the variance of the observed values of y, just plain y. So our y hat is our predictor equation. So we have come up with this crazy equation that says, look, if you told me that someone's non-dominant arm strength was 17, I can plug in 17 here, multiply by 0.936 and add 2.736, and I can predict what I think somebody with 17 would have this other number in their dominant arm. So looking here at this table, we have an actual data value of 15.7 and 16.3. That was our first one we looked at, remember? And so what we're saying here is that if we plug in 15.7 for x, and you do this calculation, you would find that it would predict that the y hat, the predicted value, would be 17.4338 for a person with a non-dominant arm strength of 15.7. Right. So this person actually had 15.7 and the other one was 16.3, but using our equation, we might predict it to be 17.4. So sometimes the prediction is good, sometimes it's not. And you see on the next one, it predicted 26.3 and it was actually 26.9. And so anyway, we calculate the standard deviation of these y hat numbers, and we square that, and we divide that by the standard deviation of the y numbers, and we get this r squared is 0.82. Remember, we had this coefficient of determination in ANOVAs, where we say how much of the variation is described by the regression, or by the difference between the groups. This is the same general policy here. And so 0.82 means that the variation is explained by this regression. And if you take the square root of that, you get 0.905. It's the same as before, like we said with ANOVAs. And what we're looking for here is a high value of r. With ANOVAs, we didn't really care necessarily. We didn't talk about that very much. We just introduced the concept that r squared was a pretty important thing. Here we actually are going to use this number a little later on down the road to say if this r is strong enough, it's high enough, then we can use this equation. If this number is not sufficiently high enough, we cannot use this equation to predict things about this data set. And so it's kind of like a p-value in a sense. We start to use r in the manner like we used a p-value, but it's not a 0.05. It's a totally different number, and it's a table value, and we're going to look it up. It kind of has some of those same things where there's a test we use with that, but the rules are much different. So you can get all of this from SPSS. So just to point out, if you did a correlational study, you look right here for your r, and there's your r squared. So again, if you take the square root of 0.819, you get 0.905. That's how those two numbers come about. And down here, these are your B1 and your B0 for the equation of your line. So see how we had our equation, our best fit line was 2.74 plus 0.94x. We get 2.739 plus 0.936x. And so that's where those numbers show up in SPSS. So by looking at these two numbers right here, you should be able to write the equation for your regression line. It's 2.739 plus 0.936x, where x is the non-dominant arm bone strength and y hat is our predicted. Again, this is our prediction. If someone came along, we would be able to predict their bone strength in case it was a value we had not seen or checked before. And so that's all I have for this lecture, and I'll do the same for Wednesday's lecture as well. And just let me know if you have any questions about this. And your homework for this section will open up, I believe, on Wednesday of this week. So I look forward to getting back to seeing all of you guys, and thank you for bearing with me this week as we do class in this unorthodox way. So again, let me know if you have any questions, and I will see you guys very soon.